Okay, good afternoon, CS61C.
Good afternoon.
Good afternoon. There we go. Better. Slight technical hitch here. All right, so we're going to plow on through our introduction to the C programming language. Just a quick review of what we did last time. We talked a lot about pointers and pointers to pointers and pointers to pointers to pointers. Pointers are just numbers. Right, they're an abstraction of the memory address, which is locations inside the machine's real memory. And they're just numbers, and we just interpret them as a different location. You can take exactly the same set of bits stored in that memory location, treat it as an integer, or treat it as a character in a string. But when we use it as a pointer, the machine is interpreting it as the address of some other location in memory. One thing we talked about last time as well, C has arrays, but they're actually very primitive. So in C, an array is just a chunk of memory, and the array name is just really a pointer to the base of that array. Somewhere else, you have to keep track of, well, how big is that array? And that's one cause of errors. Now, the compiler, the C language, in the language, you have to declare types on everything, and that's the way the compiler tries to help you avoid treating the wrong set of bits as a number versus a pointer. Right, so the type system of the language is what you're relying on to help you write correct code, and so you have to give the right type. An exception here is there's always an escape hatch in C, and for pointers you can always declare it to be a void star, which means it's a set of bits that's a pointer that points to something, anything. Pointers in general are very powerful, but they're extremely dangerous, right? So quick bit of review. So a string is just an array of characters. So where you represent some text is just a sequence of bytes in memory where each byte holds one of the characters in the string. And the way you tell the length of a string is by, as you read through it, you'll hit a 0. And 0 means I've reached the end of the string. What that does mean is you cannot have a 0 in the string itself. A 0 terminates a string. And we had this little bit of code last time, which was using array notation to find the length of a string. So this is one way of writing a string length function, strlen. You have a array, and then you just have a while loop that steps through it, reading each value. If it's not 0, you step to the next value and build up a count, which tells you how many elements there are. Question? So that's a good question. The question was, if pointers are just numbers and addresses in a machine, what happens when you move from machine to machine? The answer is, if you take pointer values, say you run a program on one machine and want to store the pointer values out to disk, for example, or on a file or a USB drive or something, bring it to a different machine, load them back in again, those pointers may mean completely nothing to the other side when you bring them in. So it's worse if you're going from, say, a machine that's running an x86 instruction set to a machine running an ARM instruction set. The memory layouts may be very different. Today we'll talk about memory layouts. But even these days, one technique that is used to help thwart security attacks is every time you run a program, the address space gets randomized. So this makes it harder for an attacker to figure out where's the really useful bits of code in your address space. So even from one run of your program to the next on the same machine, the pointer values will be different. So the pointers are just numbers, and they're really not a very portable way of expressing a data structure outside the machine. There's a technique called serialization, which you may have encountered in programming in Java, which is a more generic way. If I have some data structure, people don't care about pointers. They care about their data structure, whatever it is. Pointers are just a mechanism to represent that data structure. You can serialize that data structure out to disk in a form that when you do read it back in, you can recreate the data structure, if not the actual absolute addresses, on another machine. And that's what people would usually do if they want to save some data to go between machines. Okay, so this was a simple loop to calculate the length of a string. Here's an alternate view. This just showing you that duality between array notation and pointer notation in C. Question? Right, so that's the question is, so strings have this convention, there's a 0 at the end, so you know how long they are. what about an array of integers, an array of floating point numbers? How do you know how big it is? The answer is, you better have kept track of it somewhere else. So the C language, like I said, arrays are very primitive. You have to have somewhere else kept track of the fact that this array has 124 elements in. And that's up to you. And what programmers normally do is build their own data structure that encapsulates the storage for the array elements plus the length, for example, if they want that to be kept together. So C lets you build this stuff yourself. It gives you like very primitive mechanisms. It lets you get very low down. You have to write more code to do these things that higher-level languages do automatically for you, right? But the goal is to give you freedom to do it in different ways, to make it very efficient. So this is a different way of writing string length. So notice now, the last time on this slide, the argument was given as a char array with name s. This is a pointer to a char with name s. Those are actually equivalent. You can pass the same thing into both of those functions and you won't get a type error because they are actually the same. A pointer to a character is the same type as the base of a character array. Arrays and pointers, array names and pointers are somewhat interchangeable, right? Mostly interchangeable. So I set a pointer, internal temporary pointer p to be equal to this argument pointer. And then notice this. This is an example of concise C coding. And if you're an expert C hacker, this is how you write code. It can be a little hard to read if you're new to C, but after a while you get used to these idioms. So this says while star p++, do nothing, right? And what this is doing is, let's work through this, star p++. So first of all, the first part that gets executed is star p. So they bind, the operator star binds more tightly here. So you're going to, you're going to get the original value of p, dereference it, and read that value. That'll be the result of star p++. After that, you'll then increment p. And remember, point arithmetic. If something, p is a pointer to some type, when you say p++, it means move the pointer by one of those type. So that number of bytes in memory, characters are single bytes. So p++ will move the pointer, the numeric value will move by 1 because you've incremented by 1 byte in the memory space. Right? But this returned the value at the original value of p before you did the increment. And remember in C, true or false, if something is 0, it's false. If it's not 0, it's true. So the condition here is while the byte I read is true, i.e. not a 0, keep going. So this is actually going to scan down looking for that 0 byte. It will drop out when it hits a 0 byte because at that point the condition will be false. If the value of the byte is 0, using it in the condition of the while will make it false. It'll drop through, and then you can calculate the length like this, p minus s minus 1. Yep? The question is, what if your character was a 0? So, if s pointed to a 0 byte? So like I said, you cannot have a 0 in a string, in a C string, because that means end of string. Right, yeah. So that's what happens. It's the end of the string. You cannot, 0 terminates the string right there. Question? The ASCII value for 0. So that's not an integer 0. So it's the actual strict, in all modern machines, the 0, the null value, it has 0 encoding. The character set null character is a 0 encoding. Some old machines it wasn't. And so strictly speaking, you should compare against the null character. But most modern machines, a 0 byte means a null character, which is different than the 0 graphic for a numerical digit, a decimal digit 0. That has some other, I think it's 48 or something, is the encoding for the character 0. Right? But this is the value 0 in a character. Okay. So this is very concise code. It's just showing you the duality between arrays and pointers. Yep.
I was wondering, why is it p minus s minus 1, not just p minus s? Are you referring?
So p++, so you always increment p, regardless of whether the test passes or fails. So you kind of shoot off 1 past the end, and so you subtract 1 to get the actual length. So that was the question. Why is the minus 1 there? Okay. Okay. So when you're writing this array manipulation code in C, Quite often you use pointers, and it's quite common that you need to sort of know that you've gone past the end, like we just did. You kind of overshot by one, and that's quite common in the kind of loops you write. So the C language standard makes it permissible to have a pointer to one past the end of the array without causing something to crash in your system, right? So you can look one past the end of an array is guaranteed to not cause any damage, or no smoke will appear. Your machine won't crash if you reference a pointer one past. And this is done deliberately so those kinds of loops can be written easily, that you could be allowed to sort of run one past the end to know that you've finished. Okay? So that's just a piece of C standard mechanism. So let's talk a little bit more about what are the valid kinds of arithmetic you can do on pointers. So remember, you have to remember in your head, this is all about, at the language level, what does the compiler consider correct? Inside the machine, they're just numbers, right? This is just rules that help the compiler find bugs for you in your code, right? So the only things you're allowed to do in the C language with pointers, you can add an integer to a pointer. And like we said, what that means is it moves it by the number of bytes equal to n times the unit of things the pointer points to. So you add 3 to an integer pointer, it's going to move by 12 bytes on a 32-bit machine. You can subtract two pointers, so you can tell how far apart are these two pointers. Now, what do you think the units are of that difference? If I have two pointers into the same array, and I do a subtract, I get a value back. And what is that value? What are the units of that value? Sorry? Well, it could be bytes. What else could it be? What might be more useful? Sorry? Right, so what actually is more, in the same way that when you add an integer to it, it's in units of the thing it points to. When you subtract two pointers, the integer you get back will be the number of units of that type. So if you had pointer to int here and a pointer to int here, you subtracted to them, the number it gives you is how many ints are there between those two pointers, not how many bytes, because that's usually what you're interested in. You're working with that type in that array. You can compare pointers. Is this pointer higher up or lower down in that array? And you can compare a pointer to this symbol null, which means invalid pointer, to see that there's nothing, the pointer's not pointing to anything. So, convention, usually that's a 0 value, so 0 set of bits in a storage cell holding a pointer. That means this pointer doesn't point to anything. That's the convention we use in C programming. So everything else is pretty much illegal. You cannot add two pointers together. Not clear what that means, right? So, or multiply them or do these other things. And all that's illegal. The compiler will complain if you try and do that, right? You can force it to do that in a way I'll show you later, but there's usually no good reason to do that. It's usually a sign of an error in your thinking, if not in your coding. Okay. All right, now I just want to inject a little thing. Now you know enough to understand how you can actually get arguments to your C program. Right? So you can write a C program, you're going to run it, compile it, run it from a command line. Very common thing you want to do is pass command line arguments to your program, so it does different things on different invocations. So actually these arguments are passed in through the parameters of the main function itself. So the main function has these two arguments. The first one is just an integer counting how many arguments were given on the command line, and that includes the name of the command itself, right? If you type sort my file, argc will be equal to 2. One for the name sort and one for the argument my file, right? So this is meant to represent the prompt on a Unix machine, right? So sort my file is the command line you typed in. Now argv, arg vector, is an array of pointers to strings holding the command line arguments. Okay, so now you should know enough to understand what this means. So this is an array of character pointers, right? So you can index into the array to get the nth one of them, and each one of them is a pointer to a character array which holds a string representing that command line argument. So here's a little example. Say I type, foo hello 87 on the command line. In main, what I'll see is, arg count is 3, command itself, and 2 additional arguments. And then this will be the values I find in the argument vector. So the 0th array element has the command name foo, right? So I can tell what command name I was called with inside main. argv1 will be hello, argv2 will be 87. So this is an array of pointers to strings, right? So that array holds pointers. Each of those pointers points to a string. Each string will have a null termination, so you know where it ends, right? This is set up by the system when it starts to run your program in some piece of memory for you. This is how you can interrogate and find out your arguments. Question?
So the order of operations in the star always come first, like the brackets?
So if you read the Kernighan and Ritchie ANSI C book, there's a table that I forget where it is. It shows you the operator precedence, so how the operators bind. They've admitted later that they didn't quite get it all right. So my advice to you is use brackets. You know, it's okay to be liberal with the use of parentheses to make sure you understand the order in which things are applied, because it's usually what you want, but not always. Sometimes there are some surprises in the operator precedence. Okay, so use brackets, parentheses a lot to make sure you understand the order things happen in. Like seasoned C programmers omit them, and you just get this, you know, dense sea of characters that looks like line noise. But after a while, you get used to what they mean. But it's better style to use the parentheses if it's at all unclear. Okay, so people understand this. So one thing I'll point out is it's very useful to know what command name was used to call you. And in fact, a lot of the Unix utilities, some of them, you think there's like 5 different utilities. There's actually one program that just looks at the name to say, was I a copy or a move or a move? You know, which function am I supposed to be doing? It looks at that, and there's actually one program that's just given many different names. So when you invoke it, the program internally knows, oh, what am I supposed to be doing, right, by looking at argv0. Okay, so that's how you get command line arguments in. Hopefully this makes some sense now you've seen strings in arrays. Yep. So C is not very good. So the question was, can I do double bracket? And the reason would be... You can try it and see what happens. No, the C is actually very bad at multi-dimensional arrays. It really doesn't have good support for that. So people usually write something else, a package to help do multi-dimensional arrays in C. Okay. So now I'm actually kind of switching topics a little. We sort of focused on how you program with pointers. Now I want to spend most of this lecture trying to help you understand how the C compiler uses the memory in your machine to hold all the variables and data in your machine, right? So the questions I want to hopefully answer by the end of today is, you know, how does the C compiler determine where to put all these variables in memory? And how do I create dynamically sized objects? There's a question last time about what if my array needs to grow at runtime? How do I do that? So we'll go over that. To make things simple, we'll give you a very simple model of the machine, which is that there's only one program running at a time, and it has all of memory, right? That actually is how, you know, old machines used to be, and actually a lot of embedded systems look like this as well. But later in the class, we'll tell you about virtual memory, which is how you can have many programs running on your machine, each of which thinks it has all of memory. So if all your laptops and all your smartphones all use virtual memory, so you can run many apps at the same time, and each app thinks it actually has a complete, you know, its own complete memory system, where it doesn't really. But we'll talk about that later. So today we'll just pretend that each application, each program has all the memory in the machine, and how does the C compiler make use of that in holding your data? So I'll spend a little bit of time on this slide. This kind of is the grand summary of where everything is. So take your whole memory space, and I'm assuming a 32-bit memory address space machine here. So from address 0, which is the byte right at the bottom of memory, all the way to address FFFFFFFFF in hex, which is, you know, all ones, 32 ones. That's the highest byte address in memory. So that's 4 billion bytes of space, right, in this 32-bit address space, right? So 4 gigabytes of memory here. So how is this used? So this is a convention that we're going to use in the class. You could have different conventions. This is a pretty common style of convention. All the program, remember the program is just numbers too, right? Just a bunch of instructions encoded in a certain way you'll learn about in the next few weeks. And they're just stored in memory as well. So the program, let's just say we're going to store the program starting at address 0 and going up. That's just the program code. Above that, we're going to place what we call static data. This is variables that you know you need at compile time. Like when you write the program, you explicitly name all of these variables or data structures, and the compiler sees that when it's compiling your code and says, oh, I need to make space for these. And all that we call static data. It's stuff that is statically known before your program is run that you'll need this much space. So that'll be the next chunk of memory on top of the code. We'll put that here. Now, what's interesting is the dynamic allocation. As your program is running, it needs to allocate and deallocate memory depending on what data it's processing, what it's doing. So there's two general classes for this dynamically allocated memory. There's the stack, which we actually make it grow from the top of memory down. And then there's the heap, which we grow from the bottom of memory up. And the reason we do these in opposing directions is that we can, maximize the use of the space in the middle depending on whether you need more stack or whether you need more heap, right? So they kind of grow towards each other. And if they ever cross, you're in trouble. You ran out of memory, right? So the system will check. It'll put some actually invalid space in the middle, so it'll detect if you've overrun, okay? So these are the four major places in the memory map that stuff is stored. And what stuff gets stored where? Well, okay, the bottom is just program, just instructions for the processor. This is static data. So static data is all the variables that you declare outside of a C function. So just, in your C file, you'll have some variables just outside any function. So those exist for the whole duration of the runtime of the program. And you know how many they are and where they are, and those just live in this static data section. The stack is used to hold the variables you allocate inside a function. So when you call a function, you need a new copy of all the variables inside the function, because you can call a function recursively, right? You can call the function itself many times. Every recursive invocation needs its own unique set of space to hold its variables, right? And the way we do that is with a stack. So a stack, as we call more functions, we just allocate more space on the stack, and it kind of just grows downwards from the top of memory. And when you return from a function, we just move the stack back up again and deallocate that space. And if we call a different function, we'll reuse the space to hold different variables the next time. So the stack provides this really nice, last in, first out, allocation and deallocation of variables for every function invocation. Okay? So that's how the stack is used. It's for the variables within each function, inside the functions. What about the heap? Well, the heap is used for lumps of data that you want to dynamically allocate, but you want them to live longer than any one function, right? They're part of the data structure that many functions will operate on, but they're created dynamically, right? So, if you have a program processing a database, you probably build the dynamic structure representing the database, and you call many functions that go look in the database to do something. The database is dynamic. It's outside any one function. It's dynamic, though, so you don't know how big it is, and that's the kind of object you put in the heap. So we'll go through some examples to hopefully make this clearer, but these are the four main places that variables are stored in the memory space. Excuse me. Okay. Let's do some of the simpler cases first. So look at this little example. I've got an integer here called myGlobal. This is outside of a function. It's just sort of at the top level in my file. So it lives for the whole duration of my program's runtime. I know how big it is. I've said what it is. So the compiler just puts that into the static data section, right? It's statically known how big it is. It's always there. You can allocate it ahead of time and put it in the static data section, okay? Now inside main, main is just another function, right? So when main is called, I need to allocate space for all the variables that I declare inside of main, okay? So in this case, that's my temp. So my temp will be allocated on the stack because it's it's a local variable within a function, so it's allocated on the stack. And when main returns, it will disappear, You won't know that because the main returns your program's over.
What happens if you try and declare an array outside of any function and then resize that array within?
So the question is, what happens if you declare an array outside a function and then try and resize it within a function? So first of all, if you declare it outside a function, it'll be static, and you cannot resize it. So you just can't do that. That's one of the limitations of the stuff that's declared outside. You have to know at compile time how big they are. If you wanted to have that scenario, what you would have done is dynamically allocate the array in the first place, and then you can dynamically resize it, as we'll see later. Okay, let's talk a bit more about the stack. So here's a little piece of code. I have a function foo A, which calls a function foo B. Foo B calls foo C calls foo C, and foo C calls food, or foo D, right? Every time one of these functions is called, we need to allocate what we call a frame on the stack. And what the frame is just enough space to hold all the local variables that each function needs. And also, you need to hold, well, I was called from somewhere. How do I get back to where I was called from, right? And we'll talk about that when we go through how the MIPS assembly level works. But basically, when you call a function, remember, you can call a function from many different places in your program. And when you're in that function, you kind of have to remember, where did I come from, so I can go back there when I'm done. So that return address is also stored in this frame on the stack. All the local variables that function needs are also stored in this frame. Also, the arguments to the function. Remember we said that it's called by value? So you copy the arguments to a function, and where you copy them to is onto the stack, right? So each function can now see in its stack frame, these are where my arguments are, these are where my local variables are, and then that's the space for all those local variables within that function, right? So a function can see this stack frame of itself, plus it can see all the static data that's outside any function, right? Plus, if you pass it pointers, it can see what's in the heap, right? Okay, so people understand that. So the frame is the storage you need to run each function, and you need a new one of these for every function invocation. So let's do a little animation. So this is a different example. Main calls A calls B calls C calls D, and so on. And this is showing you how the stack is built up. So when I call main, there's a thing called the stack pointer, which you'll learn later is just a special, it's a use of one of the registers inside the processor. Keeps track of where is the stack right now. There's a stack pointer. So you call a function, the stack pointer moves down to make space. And above that stack pointer, you have a convention about where the arguments are, where the local variables are, and where the return address is, so you can get it, retrieve it from that stack pointer. Now I call into A, so I allocate more space on the stack just simply by moving the stack pointer down. So notice, allocating, deallocating space is easy. I'm just changing this one pointer to say where the top of the stack is, right? Or the bottom of the stack, I guess, is going downwards, right? And so one question people often ask, why does a stack go down? Well, one reason is you index up from the stack pointer to get at your stuff. So it's a positive offset from the stack pointer to hit the things that you're dealing with. And on some older machines, you can only do positive offsets, as you'll see later. Okay? So then maybe function A calls function B. I allocate some more memory by simply moving the stack pointer, right? Same when I do C and D. Okay, so you can just see the model. You just keep allocating this way. What this doesn't show, what you should have added here is when D returns, you just move the stack pointer up. So all that space is now free to be used by the next function call, which may be anything, right? So this is how you're allocating, deallocating the local variable space. That was the stack. So we've covered the static space and the stack space. The most complex of the dynamic ones is the heap. So C provides, in a standard library, a set of functions for managing the heap. The heap allows you to dynamically create objects, dynamically resize them, delete them on the fly, do whatever you want pretty much. The primary function is called malloc, which stands for memory allocation. So malloc gives you a chunk of bytes in memory. So this is something that takes an argument in number of bytes, right? So it's a very simple function. Give me a chunk of this many bytes that I can stomp on in memory. There's another variant we're called calloc, which gives you a chunk of memory that's zeroed. One thing to know about malloc, when you get that chunk of memory, it contains whatever was in there before. Nothing happens to it. So you have old junk in there. You cannot rely on the values inside that malloc being anything at all. They're just undefined, uninitialized, random bits, right? They're actually not random bits. They're stuff you stored in there previously, probably. If you want to zero them, you have to use the calloc call to clear them out. Once you're done with a chunk of memory, the way to release it is to say free. Free this chunk of memory. I no longer need it. There is another function called cfree. Don't use this. That's all I'll say about it. It's there for legacy reasons. It actually, if it exists, it usually just calls free. So don't use cfree. Somebody felt that if you had malloc and calloc, you had to have free and cfree, and there's actually no reason to do that. So some guys at Sun did that. Just ignore them. Don't use it. Now, if you want to change the size of a block, say I allocated a block of a megabyte, then I realized later, whoops, I actually need 2 megabytes. You can use the realloc call to reallocate and change the length of that block in memory. One thing to realize about realloc, it doesn't actually change the size of that block. What it may do, is give you a different block, copy what you have into that new block, and give you a pointer to it. So you may not be the same memory, but it will be a chunk that is the right size, right? Yeah, so be careful with realloc, because all the stuff in there might move. Why is that a problem? Well, say you had pointers to it. I created a big chunk of memory, I pointed to it, then I did realloc and it moved. And all those pointers now point to garbage, right? So you have to be very careful in using realloc. Okay, let's go over these in a bit more detail. So the malloc call, so it'll take a bit of explaining to go through the arguments to this. So this is so when you write out the function, what we call a function signature, the type of the arguments, the type of the return value. So malloc takes one argument, which is the number of bytes you want. And you might think, well, that should just be an integer, or maybe an unsigned integer. The problem is that you want this type to be, the argument to malloc to be big enough to encode the largest thing you can hold in the memory of the machine. Right? So I want to allocate 99% of my memory to one array. I'm doing some big computation. I need all the memory for one array. I need to make sure that the argument to malloc can be big enough to count all the bytes in my machine memory. And so in the C standard, there is a type defined called size_t. And size_t is a kind of unsigned integer that's guaranteed to be big enough to count all the bytes in memory. So, for example, in a 32-bit machine, size_t is guaranteed to be 32 bits at least, right? On a 64-bit machine, it's guaranteed to be 64 bits at least. Whereas on a 64-bit machine, an int might only be 32 bits, right? That's why we have this different type called size_t, which is for counting bytes inside the machine. So it's a size type. It's a type you can use to give the size of something in bytes, right? So that's a very long explanation, but basically you pass in a number saying how many bytes do you want from malloc, right? What malloc returns to you is a chunk of memory. And it doesn't know what type you're going to put in there. So it can't return a pointer of the right type. So what it returns is a void star, right? So this is just a number saying, well, this is the address where this stuff is stored in memory. That's what malloc returns. You wanted a chunk, here's a chunk, and here's a number representing where it is in memory, right? So this is a very raw, low-level interface to the memory system. One thing, if you call malloc 10 times, there's no guarantee, as you'll see in a minute, that those blocks will be next to each other in memory. They could, successive calls could return the blocks in any arbitrary place in memory. We went over this. So remember last time there was this C operator called sizeof And you really need size off in order to use malloc, right? Because say I want to allocate space for my struct. I've created some structure, right? I don't know how big the structure is on this machine. So I don't know how many bytes to ask malloc. So what I have to do is use size of that struct type to give me a number I can then pass to malloc to make sure I have a big enough space to hold that structure. One thing with malloc, you can ask it for memory, and it may not have any space. You may run out of memory, and so it's allowed to return null, which means I couldn't find you a space. So you have to check what comes back from malloc. If you just assume you have memory and keep running, you'll just end up with garbage, right? So you should always check the return type, the return value from malloc. One other important thing about malloc, as you'll see, there's a little bit of magic in how it's implemented, that it uses the empty space around the pointer that it returns to you to record how big free blocks are. So when you free up a block, you have to use exactly the same pointer it gave you that it returned from the malloc, right? So when I malloc a block, it returns a pointer, a void star that points to that block. If I want to free that block, I have to use exactly the same pointer value. Otherwise, bad things will happen, right? So here's how you would use it. Say I want to dynamically allocate space for an integer. Well, I'll declare an integer pointer, int star IP. And here's the actual malloc call, right? So malloc size of int, right? So this will tell me on this machine how big is an int. It might be 2 bytes, it might be 4 bytes, it might be 8 bytes. It might be bigger, right? So size of, though, make sure that for this machine I get a valid number that is enough to hold an int on this machine. So that number of bytes is then passed to malloc. Malloc then hopefully gives you a pointer to that block. But remember, the type of that pointer is a void star. And I want an int star. So what I can do is what's called a cast in C. So a cast in C is where the programmer takes over and says, you know what, I know I want to make this type look like this type, and I know what I'm doing, trust me, compiler. So now the compiler will say, okay, this was a void star, but you're telling me it should actually be an int star, and I will do that conversion, which actually is doing nothing. Just treat it as an integer pointer and store it in IP. Just don't complain about this allocation, right? A slightly bigger example, say I have a whole structure. Say I have a node in a tree. So I type def, I declare this type of this structure to be a tree node. So now I want to dynamically allocate space in the memory, in the heap, to store a tree node. So what I do is say malloc, size of tree node. And again, I'll cast the return type to be a tree node and store it in a tree node pointer. So now I've allocated the block and I have a pointer to it stored in TP in this case. Okay? So that's how I'm dynamically allocating memory. Once you're done with a chunk of memory, you want to often free it as well, right? So the way you do that is you pass the pointer that malloc gave you for that block into the free command, and free just is a void. So what it does is release that memory. So, you know, if you allocated this integer here, you could then free it like this. So this is a question. Say I did some pointer arithmetic on IP, the value returned from malloc. Can I then just free IP? And the answer is no. Okay.
If malloc returns null when you have no space, let's say, can null be casted into the heap pointer?
So the question is, if malloc returns a null, so the bad thing about this code, it didn't check. It should have checked whether it returns null. But yes, null is a valid value for any pointer type. So it can cast a void star null into an int star null. They're both basically 0 in the storage and memory. But yes, the compiler, null is always a valid for any pointer type. That was the question. Okay. So the answer to this is no, that you have to give exactly the same pointer that malloc gave you. You cannot just point somewhere within the object or somewhere nearby. It has to be exactly the value that malloc returned to you that you return to free. So there's an example here, so I should free this guy as well. So, you know, you should always be checking it. So notice how the amount of code you need around every malloc starts to grow if you do all the right things. Casting it to the right type, checking whether it's null. So quite often people write a function that allocates and deallocates units of the type they're working on in their program, instead of in line writing this every single time you need to allocate a tree node, you shouldn't write this in line. You should write a function that does the allocation for you and does all this error checking. So notice what's happening here is if I try to allocate an integer and I get a null, I'm just going to print an error message and crash and burn. Just stop the program right there and run out of memory. Nothing I can do. Okay. Okay. So, right. So if you don't use the same pointer when you do a free, very bad things can happen. If you're lucky, the system will stop and you'll have some hope of debugging your code. If you're unlucky, you'll just get very strange behavior. And we'll see why in a minute. But before we dive into that, I just want to give you a little example, sort of bigger example of using dynamic memory. So I'm just going to here create a binary tree that stores keys in a sort of binary tree format so I can quickly look up if I have a key or not. So here's the structure of one of the nodes in the tree. I have an integer key, and then I have a pointer to the left and right sides of the tree. Okay, so I'm going to store smaller numbers to the left of me and bigger numbers to the right of me. Okay, in the tree. So these type defs in C are the way that you give abbreviations to a type. So the abbreviation I'm going to use is capital node, but because inside the struct I haven't done this yet, I have to use struct node star. I can't use node star here, capital node star. So that's why I'm repeating the struct node star internally there to declare left and right. Okay. All right, so the tree is going to have a root pointer here. So pointer to a node is going to be the root. I'm going to initialize that to null. So I have an empty tree to begin with, right? And then I'm going to create a function, make a function that creates a new node, takes arguments for the key, the left, and the right, and creates a new node. This function inserts a new key into the tree. So it takes a key, and it takes a pointer to a node, because what I want to do is point to this root. I want to pass a pointer to that root, to this function, when I want to insert something into the tree. Okay? This will become a bit clearer maybe as you do the example. So now what I have is just a set of calls to insert, that insert 10 to the tree, whose pointer is at root, and I'm going to pass the address of root, because this insert is going to modify what's in root. Right? I'm going to modify the root pointer. It starts off as null. I need to modify it so it points at the root of the actual tree as I start entering keys into it. So I need to take the address of root. Okay, let's just try doing this. So what does insert do? Well, dereferences this tree pointer say, is the current value stored in root null? Where I am null? If so, the tree's empty. This tree where I am is empty. I'm going to create a node with a key in and just place it there, right? So I'm then going to assign to that root node, that root pointer, a node I create. So I create a node with a key and null for left and right. So what does create node do? It allocates a new node, checks to see if there's memory. If there is memory, if there isn't memory, I just die here. If there is memory, I just, notice here I'm filling in the members of that struct using that arrow notation we introduced last time. So node pointer, arrow, key, fills in the key field of the thing I point to. This I just dynamically allocated this thing here. I fill in its members. I then return the pointer to this new node. And that's the pointer I'm going to store in here. So what happens after I run this the first time, I've created this object with 3 fields, key, left, and right. And then I've stored the pointer to it in this variable root here, right? That's what happens after I run this insert 10 into root. Okay? Let's keep going. So now I insert 16. So what's going to happen here is I check. Notice I pass root. It looks in root. Root isn't null now. So if it's not null, I check to see if it's greater or less than the key in here. In this case, it is greater than. So I'm going to then recursively call this to insert this into this location, into this subtree, right? So it checks the right thing. Is it null? Yes, it's null. I just created it. And then I end up creating this node and pointing to it that way, right? And so if I go down these other examples, I just fill it in like this, right? So you should go home, study this bit of code. It might be hard to grab all this in this lecture, but this is just an example of using dynamic memory allocation in C, right? To create a binary tree. Okay. All right. So just some observations about memory map. So the code and the static parts of that memory, they're easy because they just fix size. They never grow, never shrink. You actually just allocate them when you compile a program. Stack space is pretty easy. It's just this LIFO, last in, first out, as you call and return from functions. The heap is tricky because you can allocate and deallocate blocks at any time. Okay, clicker time. So in this example, this is trying to get at how is space allocated as the program runs. So I've got a little program here. There's a couple of variables here. There's a function here. This function makes a recursive call to itself, right? Then returns the result. So the question is, this is going to call itself a few times. This is the actual call to the function. Result equals foo of 10. I want to know at this point, after the printf executes, but before the return, how many copies of X and how many copies of Y are allocated in the memory of the machine. Right? So remember, each of the variables, you need some space to hold them. I want to know how many copies of X and how many copies of Y exist in the machine at the point that you hit this semicolon here after this call. Okay? So give you a little bit of time to work through that. I'll take a few minutes. Yeah, you can try this by yourself first, then we'll do a pure instruction. Try again. Okay, I'll just go to 3:30 and stop. Okay, let's see what people thought. Okay. We have two clear front runners here. Okay, let's give you another couple minutes just to talk amongst yourself and try and persuade people to switch B and D camps. Okay, I'm going to go until 2 minutes, so get your votes in. Okay, so, all right. I guess we have a clear winner. Yeah, and D is the correct answer. So, congratulations. So, let me just go back and look at the code. So, first of all, the first easy part is, well, x is a static variable allocated outside the function. So, there's going to be one of those, right? So we can immediately discount C and E. So every call to foo, so foo goes through here and it decrements by x, so by 2. So you come around here, if n is less than 0, do that. If it's not, calculate this value, but call foo with n minus 2. So you start off with foo equal to 10, then 8, and 6, and 4, and 2, and you do call it with 0. It exits at 0, but you've already allocated the space for y. So that's why the correct answer is 6. You have 10, 8, 6, 4, 2, and 0 as the arguments of the invocations of foo, and each of those invocations needs space for y. So this would represent, 6 stack frames back to back on the stack, right? So you'd have 6 copies of y, representing the local copy for each of those invocations of that function foo. Okay, great. People got that. Administrivia, this is just the same as last time. Everybody should be able to fit in the class if you go to the right section to enroll. You can enroll first, move later is a strategy. Homework is due at the same time, right after the Super Bowl. And just to remind you, the second midterm will now be April 9th in class. Okay. So how are malloc and free actually implemented? So what goes on under the hood inside the system for malloc and free? Well, so the malloc library actually grabs large chunks of data from the operating system and then gives you pieces of that as you make malloc and free calls. And what's happening is that malloc library, as you call it, is just building its own data structure inside that space that it grabbed from the operating system. So a very simple way to implement malloc, and this could be like a project if you wanted to in a class. It's very easy to do. You just have a big chunk of memory initially empty. Every time that, you just treat it as a linked list of free space, and every time you do an allocation, you just grab a chunk and have a linked list of all the free space, and over time, it'll just fill up with chunks that people have allocated. When you deallocate, you just link over that to make one large chunk of free space. This would be a simple way of implementing malloc and free. The problem would be, though, that over time, as you allocate and free different sized chunks, you're going to get what's called fragmentation. You get little pieces of space that's not big enough for what you need right now, so you can't use them. That's one problem. Another problem is searching through this linked list to find the right size chunk can get really slow. And so it takes you a long time to find the right size chunk in your malloc library. So this is not really a practical way to do a general malloc library. So one technique people do is to keep separate pools for objects of different sizes inside. This is all hidden from the application developer, right? And one sort of generic way of keeping pools of different sizes is what's called a buddy allocator, which is kind of a cute algorithm. And the idea here is you always allocate a power 2 size chunk. So if I ask for 13 bytes, I'll get 16. If I ask for, 493 bytes, I'll get 512, right? So always round up the next power 2. Excuse me. And this makes it easy to find chunks, and also makes it easy to fuse chunks back together again and be able to reuse them. So here's all the memory, one big chunk. I allocate something that takes up half of it. I give that to something close to half the size, I give it half the size. And so on. So over time, I have these power 2 size chunks. When I free things, I fuse them back together to get the next biggest power 2 size chunk, and so on. So this makes it very easy to find the blocks and to recover and merge them later. So this avoids a lot of the problems with the standard memory allocator. Okay. So one point here is you don't need to know how malloc works inside unless you are really performance programming to the max. You really want to do the best thing possible. And often if you're doing that in C, the nice thing is in C you don't have to use the system's memory allocator. You can write your own. So a lot of very high performance C programs use their own memory allocation, right? And you better know what you're doing because it's really easy to go wrong there. But if you know what you're doing, you can write extremely fast code and you can customize your memory allocator to what your program actually needs. But if you just use a generic malloc, which is, these days, they're pretty highly tuned to work pretty well in most cases, you don't need to worry about that. The only thing is, if you notice, both of these systems, there's some internal data structure, like this linked list, for example, that the malloc library uses to keep track of what's free and what isn't. So this is the problem. If you go try and free something with the wrong pointer, the malloc library expects to find its own internal data around that pointer. And if you return it something that isn't one it gave you, it's just going to be C garbage data inside there, right? So that's why it's important to return back to malloc an actual valid malloc pointer. Okay. All right, so let's just go through a litany of all the things that can go. So telling people about C is mainly about telling people all things that can go wrong, right? It's a really, actually quite a simple language. It's elegant in its own way, but it's very powerful and hence it's very easy to go wrong. So one of the biggest ones is just using uninitialized values. You know, thinking that this value is 0 and it's not. Unless you explicitly nail it down and initialize it to 0, it isn't 0. That's not quite true. All the static variables, the ones that are one-time allocated outside of a function, those are guaranteed to be 0 when the program starts up. Right? Everything else is pretty much initialized. All the stuff on the stack, anything in the heap, unless you explicitly call calloc to clear it, everything else is going to be garbage values in there. So you have to initialize everything before you use it. The compiler can help in some cases. It will give you a warning if it detects that you're using something before initializing it, but it's not always easy for it to tell that. The problem is using memory you don't own. You thought you allocated, but you didn't. This is especially common when you allocate something as a local variable in a function, take its address, have a pointer to it, pass it to something else, and then you return from that function. That memory's gone. Well, it hasn't gone. It's still there, but it will be holding something else later. But you've passed a pointer to it, and so you'll just get weird corruption. Right? Not checking for null, and just blithely going ahead and doing whatever you did with the pointer without realizing it's actually pointing nowhere. That's another common problem. So another issue you'll get in C that isn't a problem in languages like Java with garbage collection is you can lose track of a block. Right? So this is called a memory leak. So remember, you need to have the pointer that malloc gave you to pass it back to free up the block. What happens if you somehow overwrite that pointer and forget its value? You've got no way of freeing that lump of data. So it's just going to sit there in memory occupying space. You've got no way of freeing it up after the fact. Right? So then you just create what's called a memory leak. A memory leak is basically when memory fills up with useless stuff and you run out of space to do useful things. So most of the rest of the lecture is like a whole series of horror stories about what can go wrong in your code. I'll go through some of these depending on time. We'll see how many we get through. But also, hopefully, these will be more C code examples. And if you have questions about anything else apart from the bug, happy to answer those too, just to give you some more exposure to C programs, even if they're badly written ones. Okay, so here's a piece of code. What's wrong with this? So the answers are in the slides. I suggest you don't look at the answer first, but try doing it on up here first. So what's wrong with this code? I have a couple of pointers. Pointers to integer. I allocate a block of memory to hold 4 integers. So notice I'm doing 4 times size of int because I want 4 integers space. So what am I doing here? Sorry, say louder. Right, correct. It reads from memory, doesn't own. So how do you know that?
Because it's allocated 4 integer units,
Right. Right, exactly. So here we allocated space for 4 integers. Down here what's happening is I'm saying, well, take this pointer, subtract 1,000 from it. 1,000, remember, point arithmetic is in units of the thing it points to. So go, 1,000 integer spaces lower down in memory and read from there. That was not part of the malloc, right? I allocated, 4 integers on top of that pointer. I'm now trying to read 1,000 integers below that pointer. That's nothing I should be looking at, right? Similarly here, I'm reading 1,000 integers ahead of that pointer, but I only allocate space for 4. So I'm actually allocating, I'm looking at memory that wasn't part of my memory allocation through that pointer, right? So that's a big problem. And this is the kind of thing the compiler cannot really help you with. You might say, well, it should be able to see here I allocated 4 of them, but you may pass this pointer to another function, and in that function, maybe separately compiled function, it does this thing of looking way ahead outside that block, right? So that's an area you'll see. And that's the same thing that's going down here. But what's worse here, I'm actually writing to those locations. So what's happening now is some random poor victim word in memory is being overwritten with 0, nothing to do with the space that I allocated, right? Okay. I was just explaining it, so you can use these slides for reference. How about another bad example? Oh, question? Well, this was bad code, so you... Well, yeah, you don't know where this is, so it depends how big it is, and it'd be 1,000 integers, not 1,000 bytes. It'd be 1,000 times 4 if it was a 32-bit machine, and that's how far back you go. Whether that ends up in the heap or in the static region or in the code, who knows, right? Depends how big the memory is and what the layout is. Yeah. Any question? Yes. So the question is, does this create an array of size of 4? Yes. But it does it in a very primitive way. All that you said is, I need a chunk of memory. How many bytes do I need? Well, I need enough bytes to hold 4 integers. And so it's just an array of bytes that is big enough to hold 4 integers. And remember, malloc, actually this is lacking the cast. This will work. But the malloc's return type is a void star. Malloc doesn't know what you're going to put in there. All it knows is, you want this many bytes, I'll give you this many bytes, and here's a pointer to it, a void pointer to it. You then use it as a place to store integers, and you tell the compiler that by declaring this to be an int pointer. So then you can index into it as an integer array. So now you could actually say IPR square bracket 0, and that would get the 0th element, IPR square brackets 1, 2, 3, and you could use it as a 4-element array. Question? No, you can add and subtract integers. What you cannot do is look at what I said. You can't add pointers, right? You can't subtract You can subtract pointers, but you can't add pointers. You can look at the difference between 2 pointers. That's okay, but you can't add 2 pointers together. Yes, you can subtract integers, yeah. And that just means move down by that number of units in the address. Question? Is IPR supposed to be dereferenced? Yeah, this is a bug. That should just be IPR, not star IPR. You're right. That's a bug in the slide. Somebody takes a note of that. Question? So the question is, why is it okay not to cast it? The compiler will just assume you meant to cast it. It might give you a warning. So it's not considered an error in C code because so many C programmers don't cast things properly. So instead of just crashing and burning, which meant no code would ever compile, the compiler will give you a warning. So that's why I'm saying in your code you shouldn't do this. I borrowed these slides from somebody else. You should have -w all will tell you and go through and figure out that I actually need to put a cast on all of these places. I should have checked this more carefully. Okay. Yeah, so the compiler by default will do the right thing, but it will warn you that there should have been a cast there if you turn on the maximum warning level. Question? Are IPR and IPW in the static data? Yes. Yes, they're declared outside the function. Question? Correct. So the question was, in this case, you're only reading the memory that you don't own. In this case, you're writing it as well. Now, reading it can also cause problems because it may not be a legal piece of memory, so your system might crash because you're not allowed to touch that piece of memory. Question? So the question is, what does it mean to free memory allocate the static variable? You cannot. The static variable is there for all time. It may point at something you can free, but the static variable itself is there for all time. It just lives in your program's memory space for the duration of the program's execution. Okay, let me move to another example. Oh, sorry, question?
Sort of on that same idea, when you're malloking it, that puts it in the heap, but it's a static variable. Are you making a copy of it, or what's that doing?
So the question is, if you malloc something, does it put it in the heap? Well, to be clear, static variables are always known at compile time, and so they're always just in the static space. And that's all, they're always there for the duration of your program's execution. There's no mallocing or freeing of those. If you malloc something, it lives in the heap. It'll always be in the heap until you free it. So those two words don't mix. Either they're static or they're dynamically allocated.
So if the IPR in that example is static, then what does it mean to do IPR equals malloc?
Okay, good question. So remember, IPR is a variable that's a pointer. So you statically allocate space for one pointer's worth of bits. Then when you do the malloc is returning a value, which is an address. That address is what gets stored into the space for IPR, which is static, right? So that cell, which is named IPR in memory, over time you could malloc something else and store it in that same static chunk of memory. It could point to, at different times, it can point to different things in the heap, right? Question?
So, since it makes an array for really malloc 4 times,
Yeah.
does that mean like the max you can do is just say like IPR plus 4, but you wouldn't be able to do like IPR minus anything?
Right, correct. So the question is what is legal to index here? And the answer is I've only allocated 4 elements. So I can do IPR plus 0. Remember, in C, array start at 0. And that's because the offset is 0, right? So if you do IPR points at the base of the array, you add 0 to it, you're pointing at the first element, which is the 0th element. So you can do 0, 1, 2, 3. Those are the 4 elements that are legal to access relative to IPR. Okay, let's move to the next example. Okay, instar PI. Malloc 8 times size of int, then free it. But this was called from main. So main allocates this, then calls foo. So what's wrong with this code? Yep. Actually, let's get somebody different. Anybody else want to answer? Yep, at the back. It's a memory leak. So why is it a memory leak? Right, so what's happened here, again, so pi is just a statically allocated variable that has space to hold a pointer. In main, you allocated some space and stored that pointer into pi. Then you called foo. In foo, you overwrote the value in pi with a new pointer, which is a pointer to this newly allocated block. But that meant you forgot where this block is in memory. You haven't stored that address anywhere. And so now you can't free it, right? You have no way of freeing it because you've lost the pointer to it, right? So that's going to be a memory leak now, right? You've overwritten the only place you kept track of where that block was in memory. So I can't actually free it, right? So that's the problem. Okay, I'm actually going to skip through. Let's do it in the news thing. All right. That's hard work looking at buggy C code. So I thought this was fun, talking about memory maps, memory management. So somebody just broke the record for the world's smallest functioning chess program, right? And this guy, the original, there's actually a product. Do you any guys know the Sinclair, over here it'd be called the Sinclair, no, Timex ZX81, one of the very early, very cheap computers. It had 1 kilobyte of RAM. And somebody figured out how to put a whole chess program in 1 kilobyte of RAM. So 1 kilobyte is 1024 bytes, 1024 bytes. But recently this guy figured out how to fit a whole functioning chess program into 512 bytes. Specifically 512 bytes of a boot sector on a disk, right? So you just boot up from the boot sector and you have a whole program that plays chess. So 512 bytes, that's only 64 words of 64 bits, or 128 words of 32 bits, right? An entire chess program, right? A lot of you probably can't write comments shorter than that, hopefully, right? So some of you may have names longer than that, but that's an entire chess program fitting into 512 bytes. And you can go download the assembly code from that link and have a look at this. It's written in x86 assembly code, but I thought this was kind of fun. So I remember I used to write games like this, and I remember I wrote a game that was 512 bytes as well. It wasn't chess, though, so it's a lot simpler than that. But my game had sound and graphics. So his game only has characters. It doesn't have any graphics. But I guess chess is a little harder than my game was. So, but it's amazing what you can actually fit. People forget this because what we've mostly used all the programming, all the improvement in computing power to do is to make it easier to program systems, which is good because programmer time is expensive. But if you actually spend a lot of time, you can do amazing things with a really, really tiny computer. Okay. Let's take a break there. All right. What's wrong with this code? Back to buggy C code. So what's wrong with this piece? What's wrong with free memx? Oh, sorry. Okay, let's do one at a time. Like, so free memx. Okay, yeah, so here actually what you're trying to free is the address. So notice I'm taking the address of this integer. So what kind of storage is FNH held in? It's on the stack, right? So FNH is on the stack. Here I'm taking the address of FNH, so that's fine. I can take the address of a variable on the stack, and it'll just give me the memory location that is on the stack, right? Where the stack is right now in memory, it'll tell me that, where that variable is. But then, if I pass that pointer to free, what's actually going to happen? Daniel? So where is the free function? Where does that live? Where is that piece of code that does the free? Right. So the answer was it's going to free the same address on the heap. Well, actually, there's only one unique address for any piece of memory. So that address is only an address in the stack here. But what's going to happen is that code in the free library is going to think, oh, it's a pointer in my own internal data structure. It's going to look around there to find the data it's secreted away in places you don't see around the pieces it gives you and does something with it. So it expects to find its own data structure next to that, but it won't. It'll just find your stack frame, mess that up, and probably crash and burn, you hope, because it thinks you were giving it a pointer. It doesn't check. It doesn't really know. Most of the malloc libraries don't check to see if it's actually a valid pointer. They'll just assume it's correct, assume their data is right there, and run the code in that data right there, and usually very bad things happen. And so that's actually the same problem that happens here, that you don't use the same pointer to return. And once you've done this, all bets are off for what happens when you try and call free multiple times. Right? So you can't free non-heap memory. You can't make more space by trying to get rid of stuff that wasn't in the heap. Please free this stack frame. I don't need it. Doesn't work. So here's a piece of code. What's wrong with this? So I need to explain. So this is a standard string. So there's a string library in C to make it easy to manipulate strings. It has a lot of common functions. So str n copy copies one string to another, and it will stop once it hits a 0 byte. But the n means that it won't copy more than n from one to the other. So if you don't have a 0, it will stop when you get to n. Right? There is also a str copy that will keep going until it hits a 0. And if there isn't a 0, it will copy all of memory to all of memory in an infinite loop. Right? But this one takes a number, do at least 10, up to 10. And then at the end, it just inserts the null character. So this is the correct way to write the 0 that terminates a string. \0 means this is the null character. Usually it's actually the value 0, but not necessarily, depending on the character set of your machine. Right? So so this is the terminating character. So what's wrong with this code? Yep. Right, so the problem is I only allocated space for 10 bytes, but a 10-byte string of 10 bytes of visible characters needs 11 bytes of storage, because I need another byte to hold the terminator. So you actually index one past the end of the array here and wrote a 0 to it, okay? So, this string had to go up to 11. It didn't go up to 11, right? Stopped at 10. Okay. All right, so next time you get Vladimir instead of me telling you about Lipsco.